All right. So last time we talked about parametric equations, essentially how you can wrap up all the motion in the x direction and all the motion in the y direction. Normally those things have to be treated separately, but with a parametric equation, you can dump them all into one line. So we're going to take those ideas and move forward with essentially projectile motion. So this is a specific type of kinematic movement that we can use parametric equations to actually understand. And it won't be as crazy as some of the parametric equation examples that we talked about in the last lecture. All these will all have the same form. It's just will have slightly different initial conditions depending on what we're looking at. But essentially with projectile motion, a projectile is essentially just an object that moves in 2 dimensions only under the influence of gravity. I know here it just says 2 dimensions, but for those of you that are going into mechanical or aerospace, you may have something moving in the full 3 dimensions. All the math here that we talk about will be in 2 dimensions, but you can easily just dump in a 3rd dimension as needed. It is also important to note that with projectile motion, this is just for now, just the influence of gravity. Later on, we may talk about some projectiles that are under the influence of gravity and drag, which you've sort of done in one of the labs. So you kind of have an idea of how that might work. So with projectile motion, this is also just an extension of the free fall problem. So as you drop something like Leaning Tower of Pisa problem from a couple lectures ago, same idea. Something that's just going to start from rest and fall, or start with being thrown up, get up to a point where it stops with 0 velocity for just a second, and then falls down again. Of course, second being figurative, not literal. So the mechanics that we've built so far around 1D motion and free fall, we're essentially just going to add some of that in the up-down direction and some in the sideways direction for the same object. Now, for this, there's a few things we need to keep in mind. We're going to neglect air resistance for now, because air resistance in 2 dimensions just sometimes gets a little weird. So for now, we're going to neglect air resistance, and we can do this if the object is relatively heavy, if the object is moving relatively slowly, so not like, you know, a big airplane or something that's moving like 500 miles per hour. The object also needs to be traveling over a relatively short distance. Notice all of these they have the word relative in them. So this very much is sort of like a judgment call, more or less. You know, you get an intuition of when you need to include air resistance and when you don't. These projectiles that are in 2 dimensions, they do follow a parabolic trajectory during projectile motion. So we can sort of drive home some of these points here with these 2 balls. We have a red ball and a yellow ball over here on the right that are both falling. They were released at the same time. However, there's one difference. The yellow one actually has a horizontal initial velocity. So this yellow ball actually starts heading to the right before it starts falling down vertically, whereas the red ball is just immediately released on the left. So the only difference here is the initial velocity in the x direction of the red ball. So I'll say red equals 0 meters per second, and that's really the only difference. You'll notice, because these lines are all equally spaced, when this happens, even though one of them is moving to the right, it's also falling vertically downward. These actually, they're spaced equally as they're falling down to the ground. So this really just shows you that whatever's going on in the x direction doesn't influence what's going on in the y direction or the vertical direction. The motion in the y direction is the same for both, even though the motion in the x direction is not. Yeah, so just to point this out, the red ball is dropped from rest, while the yellow ball has an initial velocity in the x direction. But both balls hit the ground at the same time, and that's just because those two directions are independent. So here's a demo. Hopefully it works. I don't know if the video itself will work, but I also included the link. Hopefully it's not too choppy. So this is just going to demonstrate that indeed this guy has a mechanism that will actually drop two balls at once. One will have a horizontal velocity, the other one will have a zero velocity in the x and y direction. So the one with no initial velocity is on the left, the one with an initial velocity in the horizontal is on the right. So hopefully this isn't too bad. You'll notice that they did fall at the same rate. They're even bouncing off the floor the same way, like same time. So that's just a physical demonstration, a real world example of, this is pretty much true for any of these kind of simplified situations that were defined on the previous slide. So those vols were identical. So the air resistance would be the same, even though air resistance may have been present because it was the same on both objects. They're going to behave the same way. And one of them did indeed have that initial velocity this way. V naught. This initial velocity did not equal 0. This one did. Yet they both hit the ground at the same time. So we've sort of already covered this, but it's good to have like in writing, so this will be the lecture notes later. If air resistance is negligible, the two objects will hit the ground simultaneously. That is because the horizontal and vertical components of the projectile are independent of each other. So this statement here is the crux of the whole thing. They are independent of each other. The initial horizontal velocity of the second ball has no influence over its vertical motion. So neither ball has any initial motion in the vertical, so they both fall the same distance h. So notice their initial velocity is in the vertical. So v initial in the y direction for both was 0 meters per second. Okay, their final distance was also the same. So with everything else held constant in the y direction, they're going to get to the ground at the same time. Let's talk about modeling these trajectories, because if we go back and look, this yellow ball here, let me see if I can change to a yellow color. Let's do this. So this yellow ball here, this is its trajectory, right? This isn't this right here is not like a x or y versus t. This is a x versus y. Because this is our x direction. This is our y direction. Right. So we have these two components. Let's see if we can model that yellow trajectory I highlighted with parametric equations. So let's think about what we know. The initial velocities in the x directions, or the x and y direction, are independent of one another. I'm going to say that a lot this lecture, so it'll sink in. In free fall, the motion in the x and y directions, did I just copy that twice? Oh no, this is good. Okay, so the initial velocities, those are independent of one another. The second point I was trying to make, which is subtle, and I almost missed it myself, in free fall, the motion, okay, so in the first bullet point, we're talking about a velocity. Here, we're talking about positions, x and y. Okay, so not necessarily velocities, but where these things are. So your x and y components are also independent of one another. And gravity is the only acceleration, like the only force essentially acting on the ball. So we haven't really talked about where gravity comes from. It's essentially just because the Earth has mass and the ball has mass. But we'll talk about that later in the course if we get to it. Right now, all you need to know is that gravity is 9.8 meters per second squared on Earth. If you get further away from the center of the Earth, so like on top of Mount Everest, that number will get slightly smaller. So in Boone, I think gravity is like 9.79 meters per second squared instead of 9.8. So there's subtle differences. But more or less around the whole Earth is always 9.8 at sea level. All right, so let's think about the x direction of any ball that we're trying to model. Okay, so this is pretty much for acceleration for any motion in one dimension. In this case, we're talking about the x direction or the horizontal. This is always pretty much the case for motion in a spatial dimension. We have position, we have velocity, and we have acceleration to deal with. Now, you'll remember from previously when we talked about just the acceleration right here, the third bullet point. Acceleration pointed down, that's only in the vertical. So there's no acceleration in the horizontal during parabolic motion like this, during a projectile motion problem. So we can actually simplify our expression here for the position, or for the horizontal position of an object. So let's utilize this fact that the acceleration is 0. This term goes away. And then we're just left with this simplified, just your position, x, plus velocity times time. Now, if we take the derivative of this, and we want to talk about not the position in the horizontal, but the velocity in the horizontal, well, when you take the derivative, the only thing left over is just that initial value. So this is just initial velocity in the horizontal. So essentially, whatever horizontal speed an object starts with, it's just going to keep that speed until either friction, until something acts on it, until friction acts on it, or maybe if it's a car, until someone pushes the brakes. Essentially, whatever you start with at the beginning of a problem, velocity-wise in the horizontal will remain the same. Now let's think about the y direction. So we need to start with all possible things we could plug in the y direction, and then we can start taking things away as needed. So here we've got our distance, which is in meters. We have this velocity, and then we're going to build up to an acceleration. So we have all three of those pieces that we've been talking about added together. Same thing in the x direction that we just talked about. Here, though, we have to be careful because the acceleration pointed downwards, well, it's the acceleration due to gravity, so we need to put that in there with a negative g because it's gravitational. So we need to remind ourselves we're going to use g. And it is in the negative direction generally, so there's our negative g. Now we can plug that in down here. And essentially we have, so in the y direction, we actually can have all three things. We can have an initial position, we can have an initial velocity, and we can have an acceleration. So the y direction function here is going to be a little more complicated than in the x direction. And that's just because of our acceleration due to gravity is in the vertical. Same thing again, we can take a derivative and talk about the velocity in the vertical, and that's given right here. Now all we have to do is just plug this stuff into our nice parametric equation for the I hat or x direction and the y hat or j direction. Sorry, the I hat or j hat, which would be the y direction. So this is our x direction. This is our y direction. Same thing with the velocity when we take these derivatives. Here's that constant velocity in the x direction or the I hat direction. And here is our expression for the vertical velocity and how it changes over time. All right, let's think about an example here. So let's model this setup over here on the right. Let's model this with a parametric equation. So we'll start with their general form here. And then we'll just start plugging in what we know. Well, it looks like from this picture, without really reading anything yet, we'll just take what we can from the setup here. It looks like we're starting from the origin, so where x equals 0 and y equals 0. So our initial components, 0, 0. Well, it looks like we have an initial velocity. All right, so here's our initial velocity. I'm drawing it in orange. I don't know what the length of this vector is because in the image it's already broken down for us. So here, this is our Vx. And this is of this velocity vector here I've highlighted in orange. And here's our Vy. Notice that this here, this velocity chunk in the x direction is 9.8. This is not the acceleration, okay? It just so happens that the velocity in the x direction has the same magnitude as the acceleration in the vertical, okay? So the fact that there's a 9.8 here and acceleration is negative 9.8, in this problem is just a coincidence, okay? So don't be looking for a connection there. But since we can break down this velocity vector from the initial velocity, we can write down its components. So we know in the x direction it's positive 9.8 meters per second. In the y direction, or the vertical, it's 19.6 meters per second. Going on, we already know some stuff about acceleration since this is a projectile motion problem. We know in the horizontal there is no acceleration, there's no influence. Because in the vertical we have gravity. There's no accelerating influence in the horizontal. So acceleration in the x is 0, but acceleration in the y, negative 9.8 meters per second, down as usual. Now we can take all this crap we know and plug it into our parametric equation. All right, so here, looks like I've already gotten rid of the initial x position, and we're just left with the velocity times delta t, and this is in the x direction. For the y direction, we also have the initial velocity, vy. This is how fast it's going upward. But then we also have this, a lot of old classical physics textbooks call it essentially like a retarding force or retarding acceleration. So the thing slowing this down is g, our gravity in the y direction. Now these, it's kind of gross with all these letters floating around in our units, but you do need to keep your units in your math all the way through. That way, once you get used to doing that, it makes finding typos and stuff so much easier. And it's also a good way to check yourself. You always need to make sure your units are working out as you go. So it's a good practice to keep in mind of. So notice what's going on over here in this picture. So every second, the velocity is getting smaller. Even when it hits 0, it starts turning negative. That's technically smaller. So what this acceleration is saying is that every second, 9.8 meters per second is subtracted off the velocity. Okay, so here, let me change colors. Let's see. We have our initial, oh, that's like the exact same color. Let's do red. So here we have our initial velocity, which is 19.6 meters per second up. Okay, well, after 1 second, we have to subtract some off because acceleration is negative and is taking that away. So after 1 second, we have to subtract 9.8 from the downward acceleration, which means we're just left with 9.8 meters per second upward. Okay, well, acceleration is still acting in the negative direction. So here, notice at the top of my arc, I have no vertical velocity. I don't have any pointing up. I don't have any pointing down. All right, so here, for just one moment, one brief moment, my vertical velocity is 0. Now watch what happens once I get past my peak here. Once I get over here, I have to yet again subtract gravity. So my velocity is speeding up, but in the negative direction. Okay, and then 1 second later, I have to subtract that same amount of acceleration to my velocity because the acceleration is changing it, making it more negative. So you can see I've got 2 red arrows on the left pointing up but getting shorter. Right in the middle, I have no vertical acceleration, and then my acceleration becomes negative and starts increasing again. And the thing that's changing the shape of these red arrows, all that's gravity. Gravity is always subtracting from your vertical or your vertical speed. Even when your vertical speed is 0, like at the top, gravity is going to keep subtracting and make your vertical speed suddenly negative, and it'll keep getting more and more negative. Now, if we look at our velocity in the horizontal, it's kind of boring. So right here, the horizontal component of our initial velocity is 9.8 meters per second to the right. After 1 second, it's still 9.8. After 2 seconds, still 9.8. After 3 seconds, still 9.8. And 4 seconds, still 9.8. So what this is telling us is there's literally no friction, no air resistance, no drag, no anything that's actually affecting our horizontal movement. All right, let's look at yet another example. So a stuntman drives a car off of a 10-meter high cliff at a speed of 20 meters per second. How far does the car land from the base of the cliff? So remember our 4 steps. Model, okay, well, we're doing that now. We're going to use kinematic equations. Visualize, well, here I've got it drawn out. It's very useful. For full credit on problem sets, you should always draw a quick sketch of what's going on in these problems. But what we want to know here specifically is essentially, what is this horizontal distance? Well, we've written out everything we know. It looks like our origin is right here at 0, 0. So that means our initial x value, well, our x component starts on the origin. However, our y component, our y coordinate, it's up here. It's 10 meters in the vertical. So that means our initial position is actually 0 horizontally and 10 meters vertically. And we have that represented right here. 0 horizontally and 10 meters vertically. Well, another easy thing we can jump onto right now is we can go ahead and say that our acceleration in the x direction, we already know that's 0. This is a projectile motion problem. We're not dealing with any sort of forces in the horizontal. That means our vertical acceleration, well, it's a falling object, so it's going to be gravity. I should be more specific. It's a falling object on Earth, so that means it's going to be just g, negative g, essentially. Now, something else you got to think about is we can also know our final values. We don't just always know the initial stuff. We can also look at the setup of the problem and know what's going to happen at the end. Well, we can see here that the amount in the vertical direction that this car is when it hits the ground is 0 meters because it's on the ground, even though it started above. So that's some more information that we can use. Another obvious one is t, the initial time, t0. Well, that's just 0 seconds because we were allowed to pick that. So we can pick the initial time to be t0. Our initial velocity up and down in the vertical, well, the car's not flying off into space, so we have no vertical velocity. The car's not digging itself into the ground, so we have no negative velocity downward. So we've got 0 meters per second in the vertical. We do have this speed where this car is driving to the right in the positive x direction. We do know that it is 20 meters per second squared. Okay, so this is pretty much everything we can glean from just this picture. This is why drawing pictures is important, because it lets you visually see and sort of check off what you do and you don't know. All right, well, let's talk about the x direction stuff, so to speak. Well, we know the equation in the x direction because from our parametric setup just a few slides ago, we know that it's simplified. It's just an initial position plus a calculation to get an additional distance? Well, we can plug in everything. We know our initial distance is 0, starting from the origin. We know our initial velocity in the horizontal is 20 meters per second. And we can also plug in our initial time, that's just 0. This is our delta t, just as a quick reminder. Anytime you start with your initial time being 0, your delta t just becomes a regular old t, and I've shown that over here. So when we simplify, it's literally just your initial velocity times how long you're traveling at that velocity. Now the y direction is a little more complicated. Here we have all three components sort of at play. We have a position component, a velocity component, and an acceleration component in the vertical. So we have our initial 10-meter height from the cliff. We also have our initial velocity. Remember, it's 0, so it's going to make this term go away. And then we also have our initial time and our acceleration due to gravity. All right, so from here, what we can do is we can simplify this first line here. Because notice, we have pretty much everything in these equations. So everything here is filled in. Everything down here is filled in. The only thing we don't know is just a t final. So we have no idea what our t final is. So the idea is we can't directly calculate this x value that we wanted. We can't directly calculate this yet. We can calculate when it happens, but we can't yet calculate where. So let's use our y direction information to calculate not where, but when the car hits the ground. If we know when, we can back calculate to get where. So again, let's take this information here from our y direction and just plug in what we know. Well, we know this thing hits the ground, so that's its final y value is 0 meters. And then everything else on the right-hand side of the equation just comes along for the ride. Now we just solve for t, and I won't do the algebra here. But essentially, when you solve for t final value is 1.43 seconds. So this didn't answer our question of how far away does the car land from the base of the cliff, but it gives us some more information. It tells us when that happens. Okay, so this is not where, but when. We can use that to actually figure out the where now. All right, so essentially the time required for the motion in the y direction, so the amount of time it takes to go from the top of the cliff to hit the ground, that t value, the 1.43 seconds, is also the same amount of time that this car is traveling in the x direction. Now we can just simply use that very simple equation for the x direction motion and plug in this time that we got. So remember, this is our t final. So all this is saying is that the car in 1.43 seconds hit the ground from the top of the cliff. Okay, well, it's also traveling 20 meters per second to the right. How far did it go in the horizontal in 1.43 seconds? And it turns out that value is 28.6 meters, which to me, just doing the fourth part of our problem solving where you assess, that sounds a bit far, but that was also essentially a 32-foot high cliff. So maybe, yeah, I guess about 100 feet might make sense. I don't know. It seems pretty far to me. But the math works out, so we're going to assume it's correct. So this, again, I've said it several times, but I want to point it out some more. There was no time given. The amount of time this car was in the air was not given in this problem. So we don't know the time of flight, or TOF for short. We don't know the time of flight, but we were able to get it. So anytime you don't know how long a projectile is moving, you can usually calculate it. So we were able to determine the TOF from the motion in the y direction. So we were able to pull that just out of one component of the motion and then apply it to both. We can do the same thing in our parametric equations. So essentially the idea is we can take our parametric equation from this example, right? So this is essentially the custom x and the custom y for our problem of a car running off of a cliff. Okay, this won't work for anything. These were the equations we built for this example. You can rebuild these equations for whatever example you're looking at. So we can start with our x and y for our example. Okay, we don't even need to know the values of these variables. We can just leave them as variables. All right, well, what we wound up doing was essentially taking one equation, solving the time, and then plugging that into another equation. So let's do the same thing again without numbers. So we can take one equation. So here, x, solve for time. You can see all I do is just divide the velocity over. Okay, so I've taken my equation, solved for time, and then I simply just plug it in. So this was where my t was. So instead of a t squared, I still have my t, it's just represented symbolically. It's not an actual numerical value. So I'll plug that in and I get this fancy equation out. So this literally is y as a function of x. So instead of, in previous lectures, we talked about and plotted how y changes as a function of time, or how x changes as a function of time. Remember? And then we switched from plotting things with respect to time. We started plotting y as a function of x. So this boxed equation right here, if you were to plot it, is literally this right here. It's literally the trajectory of this car. Because look at how the axes are labeled. This is literally a y as a function of x coordinate system. So what I've boxed in this next slide is essentially the plot of this car's trajectory right there. So you got to be careful. Sometimes things like y is a function of x, sometimes y is a function of time, sometimes x is a function of time. So you got to watch what's being said mathematically. All right, one more example. So this one should be fairly straightforward. So a baseball is hit at an angle theta and is caught at a height from which it was hit. Oh, sorry. A baseball is hit at an angle theta and is caught at the height from which it's hit. That means whatever height the bat hit the ball, the glove that catches this ball is going to be at the same height as when the bat hit it. So there's no weird, there's no cliff problem, so to speak. Where you start in the vertical is going to be the same in the vertical when you end. All right. So if this ball is hit at a 30-degree angle, how fast does it need to go to actually travel 100 meters? Yeah. So if we hit this thing at a 30-degree angle, so I'm actually going to include that over here in the plot. So if we hit this thing at a 30-degree angle, well, what does our velocity up here, our initial velocity, what speed does that need to be? Ooh, that might be a little hard to see. I'm going to change these to red. Yeah, so we have 30 degrees here. Now, what is the magnitude of this velocity that will let us get 100 meters away? So 100 meters in the horizontal. All right, well, let's start setting things up. So we know we're starting from the origin. Now this is really nice because that gives us a 0 meters in the x, a 0 meters in the y. You can see that here. Notice how you can write it very compactly. You can just say x naught equals y naught equals 0 because that's where you're starting. There's no magnitude of the position component at the beginning. We're given this angle from which it leaves because we get to decide when we start our stopwatch. We can start it at 0 seconds, so t naught is 0. That also simplifies our equations a bit. We don't have a delta t anymore. Now all we know is that by the time the ball gets over here and lands, well, we know what its coordinates is going to be. It's going to be 100 meters away from us. And it's not mysteriously floating up in the air and it didn't drive itself down to the ground, so its vertical position has to be 0 meters. All right, and we have that included down here. So it looks like we have about everything except that initial velocity. We know we hit it at 30 degrees, we just don't know how hard we hit it. So let's look at our x component and our y component. All right, so here you'll notice that I've already taken out the xi plus part because that's usually here, but we already know that it's 0 meters. I didn't even bother putting it in. And all we're left with is the x component of that initial velocity. We don't know what that initial velocity is, but we do know we want the x component. So this piece here, I can draw it in on my plot. That's my x component right there. So it looks like I've got my x set up. It was pretty easy. Now let's move to the y. Okay, well, I know my y final, which is right here. I know this thing lands on the ground, so my y final has to be 0 meters. There's no initial piece. There's no y initial. Both of these are 0. So that's taken care of. The only thing left is essentially the vertical component. I think I want to do this maybe in green. So I need the vertical component of my speed, so how fast the up part of this vector is. I don't know what v0 is, but I do know how to calculate the vertical component of it. Right, and that's just going to be sine of the magnitude. So that's this piece right here. Oh, good, you can see that, I think. Okay, so we want that vertical piece. And then this is a projectile motion problem, so I've got to include some gravity. So there's my gravitational component. Now, what we can do is essentially if we just look at this piece here, essentially the right-hand side of this statement. We know the right-hand side of the statement has to equal all the other pieces. We know this thing has to equal 0 meters. So now let's just solve for v0. See, we can actually move gravity over. So plus 1/2 gt squared plus 1/2 gt squared. That's going to give us this line right here. 1/2 gt equals v0 sine theta. Essentially, I just canceled out one of the t's as well. Now let's solve for t. Remember, that's the thing. We want a horizontal distance. We want this final x value, but we need to find out when that happens before we can find out where that happens. We still need to know this t final. So when we solve for t, we don't know what any of these numbers are. We don't know what v0 is. We know what g is, but we're going to leave it as g. We know what theta is, but let's just leave it as theta. When we solve for this, we know that we can say one statement here. So this is us solving for t. You guys can do the algebra. I'm not worried about it. So solve for t. So here's the thing. When we solve for t, we get something really interesting going on here. So the ball has a y displacement of 0 meters. That means it is on the ground at 2 places. It is on the ground at t equals 0. So when the problem first starts, and then it is on the ground at this value. Like I said, we may or may not even know what all these are, but we do know that this is an expression for when that ball is essentially having 0 vertical displacement. I know I've been saying on the ground, but in reality, this is the height that the ball was hit and then the height that the glove was. But the physics of the problem is the same, whether it's bat and glove or literally the ball leaving the ground and hitting the ground again. The way we've set our origin up, it's the same thing. So it's reasonable to call this being on the ground, even though if we were to watch this happen, we'd see that it isn't. But the physics doesn't know the difference. The physics doesn't care. This could be 2 miles in the air, and it's going to work the same way. So yeah, we have these two different times. We have our initial one, that's trivial. We know that it's at the origin at t equals 0. We defined it that way. But then this one over here, we can use this anywhere. At this time, this object's going to be on the ground. Now remember, this only works if you have this set up. It only works if you're on a horizontal surface. Only for horizontal. So the car jumping off the cliff, well, that was like two different places. The height for the start and the finish of the problem, they were very different. But anytime when the start and the finish in a projectile problem is the same, you can use this equation no matter what to find where it is the ground. So let's keep going. We're almost there. All right, so this is now secret information because I'm erasing it. You may want to pause and write that down real quick. So now we can take this time because we got this from the vertical. Let's plug it into the horizontal. Okay, whoops. Okay, so this is from y direction. Now we're going to plug it into t, right? So we're going to plug it into where t was in our horizontal. Okay, now we have to do some fancy footwork here. So I plugged it in and I just rearranged. I brought the v out. Notice that there's two v naughts, so now it's v naught squared. We have a sine theta and a cosine theta floating around. So it turns out that you can actually take 2 sine theta times cosine theta, and that is just equal to sine 2 theta. So I've used this trig identity. Ooh, that may be hard to read for you guys. I apologize if it is. It really just depends on which screen I'm looking at, how it looks. But we can take this this trig identity, which you all probably learned from pre-calc, and essentially we can just simplify all the trig crap in there down into a nice simple expression, and it's that sine 2 theta. All right, so we have this really pretty statement that we can say our final position, xf, can be calculated if we know the initial velocity, the angle that this thing left the origin from, and gravity. Well, we actually know about all of this stuff except the initial velocity. Remember, if you go back and read the problem, this is the thing we wanted to know. We wanted to know v naught. So let's solve for v naught, okay? So we'll take this expression, rearrange it, okay? And then if you look here to the right of v naught equals, we know all this stuff. We know that gravity is 9.8 meters per second squared. We know that our final distance is 100 meters. And we also know that angle is 30 degrees. So now we just dump all the numbers in. And it turns out that if we hit this ball and it leaves our bat at 33.6 meters per second, which is very fast, if it leaves at that speed at a 30-degree angle, it's going to hit the ground or at least be caught at the same level 100 meters away. That's really far. That's like a little more than a football field. So just one last little tidbit. So there's a cool piece of symmetry here. Essentially a projectile that's launched at theta or 90 minus theta will travel the same distance. So let's draw this. This is actually pretty handy to keep in mind. Okay, so you'll notice here, our first theta, let's say is 15 degrees. Okay, well, if we launch at 15 degrees, here's my endpoint. Okay, well, let's see, 90 minus 15, well, that's 75. So just like the 15, if we launch at 75, Boom, same endpoint. Let's try it again with 30 degrees. All right, so we launch at 30 degrees. Track it. There's our endpoint. Okay, well, let's see, 90 minus 30 degrees, well, that's 60 degrees. Well, even if we launch at 60 degrees, same endpoint. So there's a neat symmetry about these projectile motion problems. And then, of course, if we launch at 45 degrees, well, 90 minus 45 is still 45. So it turns out that another thing you should keep in mind, if your starting point and your ending point for a projectile motion problem are the same, 45 degrees will always give you, 45 degrees will always give you your maximum distance every time. Now, what's really weird is if you start on a platform, or like the car problem where your initial position is higher or lower than your final, it's not always 45 degrees that's going to give you your maximum distance. So that's just something to keep in mind if you're trying to be clever on a homework problem or something. So with that, I think that's pretty much got everything covered as far as the basics of projectile motion problems. It's just essentially some simple parametric equations and accounting, essentially, making sure you know what you have, what you need, and then filling in the blanks from there. Don't forget that the time is your connection between the x direction and the y direction. That'll always be your link between the two. Otherwise, motion in the x direction and the y direction, or I hat, j hat directions, they're always independent of each other. All right, that's it. And as always, if you have any questions, please let me know.